Hi, I'm Kishihi, and this presentation is about analysis of functional and technical rationales for MLOps in the development and operational of machine learning system. This presentation will introduce machine learning application and their challenge, and explain how MLOps has been developed to address this challenge. We're also going to discuss the current MLOps technical and human factors and how this factor bring limitation and how we can mitigate some of them. So first, what is machine learning? Machine learning has become a core technology across industries such as healthcare, finance, retail, and public services, supporting decision-making, automation, and data-driven insights. It refers to a branch of artificial intelligence in which systems learn patterns from data and improve performance over time without explicit task-specific programming. Machine learning methods are commonly categorized into supervised, unsupervised, and semi-supervised learning. Successful deployment depends on high-quality data, appropriate model complexity, and model interpretability. As a result, machine learning is best understood as continuous life cycle from data collection, preparation, model training, evaluation, deployment, and continuous monitoring, where models must be regularly updated as data and environments evolve. However, only 13% machine learning projects in enterprise eventually reach production based on surveys and research. Machine learning are having challenge, and using the traditional way is not feasible for the current situations. So what is the challenge they are facing right now? Many machine learning processes still rely on manual and on-hand operations, making it difficult to scale and maintain. Such practice introduce implicit technical debt, including fragile data dependency and inconsistent workflows. Reproducibility is another major challenge, as insufficient version controls and experiment checking make models hard to reproduce, audit, and iterate as they move from research productions. In addition, real-world data distribution evolve over time, causing model drift that requires systematic monitoring and retraining. These technical issues are often compounded by fragmented organizational structure, where data scientists, engineers, and operation teams work with disconnected tools and processes. That's increased deployment risk. Together, this challenge highlighted the need for structured operational framework to manage the full machine learning life cycle. It given rise to MLOps. So what is MLOps and what is core principle and component of this system? Surveys show that 70% of organizations have already invested in MLOps tools and platforms, reflecting the value of MLOps in successfully implementing artificial intelligence projects. MLOps is a variant of DevOps concept, originally developed and addressed continuous deployment issues similar to those of traditional software have been used for over 4 decades. Unlike DevOps, MLOps focus on problems specific to machine learning, including continuous training, model monitoring, testing, and version control of data and models. The integration of machine learning with operation bridge the gap between the development and operation phase of machine learning lifecycle. It enables organizations to streamline the entire process from model development to deployment and the maintenance. It is used to manage the end-to-end lifecycle of machine learning system. So based on the summary of research, the implementation of MLOps requires adherence to 9 principles. Its overall structure can be divided in 4 layers: code management, process automation, model development, and deployment and monitoring. As shown in figure, first, the development and code management layer use code repository and CI/CD pipeline to enable continuous integration, automated deployment, version control, and team collaboration. Second, the process management layers relies on workflow orchestration to coordinate machine learning pipeline, ensuring reproducibility of experiments and support continuous training and evaluation. Third, the model development and data management layer manage model training, feature, and model version through training infrastructure, feature store, and model registries. While metadata checking ensure transparency and auditability. Finally, the deployment and operation layer handle production deployment and continuously monitors models' performance, feeding results back into the pipeline to enable the automated retraining and ongoing optimization. A crucial and indispensable part of MLOps is humans and skill. MLOps is an interdisciplinary teams collaboration process, and the interactions among different roles are essential for designing, managing, automating, and operating machine learning systems in production environments. As shown in the diagram, 7 key roles are involved in an MLOps environment: business stakeholders, solution architectures, data scientists, data engineers, software engineers, DevOps engineers, and the most important, machine learning engineer. And we can also call it machine learning operation engineer. The roles combine the responsibility of multiple roles, thus possessing cross-domain knowledge. This role integrates the skill of data scientists, data engineer, and etc., and also the backend engineers. This cross-domain role is responsible for building and operating machine learning infrastructure, managing automated machine learning workflow pipeline, and model deployment to production and monitoring models and machine learning infrastructure. Overall, MLOps automated key phases of the machine learning lifecycle, including data preparation, model training, deployment, and monitoring. The benefit of MLOps include: first, automated pipeline reduce friction across the machine learning lifecycle, allowing models to be deployed and tested more quickly. Second, continuous monitoring and feedback loops improve the model reliability by ensuring model remain accurate and adapt to changing data. Third, MLOps enhance collaboration by enabling closer coordination between data scientists, machine learning, engineering, IT team, and also even the business people and business team. Finally, automation helps reduce cost and technical debt by minimizing human error and simplifying long-term model maintenance. While MLOps offers numerous benefits, its implementation involves significant technical and human factors. We can categorize these barriers into 2 main categories: technical and human factors. Human factors encompass operational, business, and organizational barriers. So what are some of the typical technical challenges of MLOps in various organizations? First, data complexity and governance and make it difficult to manage large, involving data sets while ensuring data quality and regulatory compliance. Second, automation and workflow orchestration are hard to implement reliably, as integrating multiple tools across environments increase architecture complexity. Third, management tool and managing model version and artifact become challenging at scale, affecting reproducibility and auditability. In addition, integration and scalability issues arise from fluctuating workloads, legacy systems, and high infrastructure costs. Finally, continuous monitoring is essential but complex, as data drift and system failures require real-time detection and retraining to maintain a stable performance. And also, human factors also play a very critical and necessary role in the success or failure of MLOps. From an organizational perspective, many challenges stem from skill gaps, cultural resistance, and weak governance. MLOps require close collaboration across data science, engineering, and operations. However, organizations often lack the necessary hybrid expertise and shared ownership structure. Without standardized practice and clear accountability, MLOps initiatives struggle to scale. At the operational level, coordination and communication issues are very common to see in different situations. Misalignments between development and operation team, combined with limited continuous learning and weak change management, often leads to deployment delay and inefficiency in model lifecycle management. And the last one, from a business perspective, MLOps adoption is further constrained by misalignments between technical goals and business strategy. Organizations may struggle to justify return on investment, while ethical, regulatory, and also privacy risks increase, especially in multi-organizational environments. So how do we learn the key lessons from successful and unsuccessful MLOps implementation to mitigate these issues? First, Many limitations of machine learning operations stem from data complexity and data governance issues. This problem can be mitigated by establishing a standardized data governance framework, supplemented by automations, data validation process, and quality checks. By checking data lineage and metadata throughout the machine learning lifecycle, organization can improve the data reliability, reproducibility, and compliance, especially in regulated and or cross-organization environments. Second, a unified automation strategy can reduce the complexity of automation and workflow orchestrations. Successful MLOps implementation integrate machine learning pipeline into existing CI/CD workflows, rather than treating them as separate systems. Standardized environment through containerization can further reduce compatibility issues between development, testing, and production environments. Third, adopting a centralized model registry and integrated version control system can alleviate the challenge associated with model version control and artifact management. Managing both data and model versions simultaneously ensures traceability and reproducibility, while systematic artifact checking facilitating auditing and long-term maintenance. Fourth, adopting cloud-native architecture and reference design can address integration and scalability challenge. Scalable orchestration frameworks enable organizations to dynamically allocate resources based on changing workloads, while standardized APIs and toolchains improve the internal operational ability between systems and teams. Fifth, infrastructure resource pressure can be alleviated through resilience, cloud infrastructure, and automatic resource scaling. Proactive capacity planning and workload optimization help balance performance requirements and operational cost constraints. Six, performance instability caused by data drift and content drift require continuous monitoring throughout the model lifecycle. Effective MLOps practice embedded real-time monitoring, anomaly detection, and automated retraining mechanism into production system. This ensures the model remain robust, reliable, and compliant over the long term. Human challenge in MLOps often stem from the weak cross-functional collaboration, unclear governance structure, and misalignment between machine learning initiative and business strategy. This limitation can be mitigated by fostering collaboration among data science, engineering, operations, and business teams through the shared workflow and aligned objectives. Establishing clear governance and accountability across machine learning lifecycle improves transparency, reliability, and compliance. Finally, aligning machine learning objective with organizational strategy ensure the MLOps effort focus on high-impact use cases, enabling sustainable deployment and long-term business value. In summary, this analysis explored the functional and technical rationale for adopting MLOps in the development and operation of the machine learning system. While machine learning is widely used across industry, most models fail to deliver long-term value in production due to the fragmented workflow, limited repeatability, scalability constraint, and weak governance mechanisms. MLOps emerged to address this challenge by operationalize the entire machine learning lifecycle through automation, CI/CD integration, standardized workflows, and cross-functional collaboration. This improved deployment reliability, scalability, and team coordination. However, this analysis also showed the MLOps is not a panacea. While it addressed many shortcomings of traditional machine learning practices, it introduced new technical and organizational complexity, including data governance challenge, automation overhead, infrastructure resource pressure, and performance instability. Importantly, lessons learned from both successful and unsuccessful MLOps implementation demonstrate that these limitations are not inherent flaws, but rather challenges encountered during the implementation. This challenge can be mitigated through strong data and model governance, scalable cloud-native infrastructure, a unified orchestration platform, continuous monitoring and automated retraining, and clear division of responsibility between technical and business teams. In short, MLOps does not eliminate complexity, but rather make it manageable. Its true value lies in helping organization advance machine learning from experimental prototype to robust production-ready system through a well-designed engineering system, and also the organization coordination. So here is all of my presentation, and here are the reference I use to support this analysis. And thank you for your listening.